Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to go through how to write a system of equations for a circuit. And what I'm going to do is we're going to take a look at this example here where we've got this circuit driven by this 24 volt battery. We've got a 5 ohm resistor here, a 3 ohmer here, a 1 ohmer here, and another 6 ohmer that I threw in just for fun. All right, so when you're analyzing a circuit, the first thing we have to do is put currents in, and you have to know how many currents to put into the circuit. So one thing I like to point out is the current is going to be the same anywhere from here to here. So there's going to be one current in that region. There's going to be another current in this region. Then we're going to have another current in this region. So this problem has 3 currents. So the first thing you do in a problem is you draw the 3 currents, usually assuming positive charge carriers. It's fairly standard, fair physics convention to assume positive charge carriers when you're dealing with circuits. So I'm going to start here with this 24 volt battery that's driving most of this circuit here. This is the positive terminal, which means it's at the highest potential. Assuming positive charge carriers, that's going to give us a current, which is going to be this way, which I'm going to call I1 here. We can call this anything we want. Now the reason it's to the right, current goes from higher to lower potential, and no doubt this terminal is going to be the highest potential in this problem. Now that value of I1 is going to be good, again, anywhere in this branch. So I could actually draw it anywhere if I want to put it here up or here down. That's perfectly fine. All right. Now this I1, when we get to this point, there's going to be kind of a divvying process. Some can go through this branch, some through this branch. So we're going to have a new current in this branch, which is going to be most probably in this direction, which I guess I'll call I2. And again, I2 will be good anywhere in this region. Next, we're going to have to deal with this region. We're going to have another current here. I'm going to go ahead and draw a current, which I believe will be in the following direction. Call that I3. Where the value of I3, whatever it is, that's going to be good anywhere in this branch, right to that point. Now, when you're dealing with these complex circuits, and this is not what I would call a complex circuit, but when you're dealing with a system that's got many branches in it, and you have 3, 4, 5, 6, there's really no limit to the number of currents you could have. Sometimes it'll be clear which way the currents are going to be, other times it won't. If you don't know a current direction, you are free to guess a current direction. As long as you are consistent throughout your work, what will happen is when you finally solve the problem and you get your currents out of it, if your assumed direction is correct, you'll get a positive number for it. If your assumed direction is incorrect, you'll get a negative number. All right, so we've got our currents drawn. Another thing that I like to do before I do anything else is color code potentials. So I'm going to start with the highest potential and work my way down. So this terminal here is the highest potential in this problem, no doubt. And this is all going to be one potential up to this point because this is all conducting material. If you're not familiar with my IFACS videos, go back and take a look at that. And one of them was no electric fields in these conductors, which means the conductor itself is an equipotential. There will, however, be a potential difference across this resistor. So by the time we get to the other side, we're going to be at a new potential. So maybe I'll color that one, maybe orange. And that potential will be the same up to this point, down along through here to this point. I can draw that a little better. And again, the reason it's the same is this is all conducting material. The conductor itself is an equipotential. Right, when we go across this resistor, we're going to drop in potential again. I'll draw that one maybe yellow. This is all going to be one potential. When we go across this 6 volts, we're going to increase in potential. Now this is going to be all one potential because this is conducting material up to this point. So I'm just going to leave that the way it is. We'll just leave that black. So I've got my color codes on my picture here. And anytime we change color, we're going to change in potential. Now, equations and how do we write them? So imagine that I start here. And I kind of walk along this circuit. I always imagine like a little ladybug or something walking along the circuit. And imagine I walk along this path and I come back to the same spot. If I get back to the same spot, that means I'm at the same potential I was before. And that means if I keep track of all the potential differences as I walk this path, they have to sum to 0. And that's the first type of equations we typically use to write what are called Kirchoff's equations. And the first is what are called loop equations here. So I'm going to imagine a closed loop here. And I usually imagine a ladybug walking along this system here, coming back to this point. So I'm going to imagine starting here, and my ladybug now is walking, walking, walking. When that ladybug goes across here, that ladybug is going to go up in potential by 24 volts. Ladybug would be at the red potential. Now as that ladybug walks along this path, when that ladybug goes across that resistor, that's going to be a drop in potential. Remember, current always goes from higher to lower potential. So we're going to drop by an amount I1 times 5 ohms. And this is by Ohm's law. Voltage equals current times resistance. So our ladybug would now be at this orange potential. Ladybug's walking, 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 comes across here. When the ladybug goes across this resistor, it's going to drop again in potential by an amount I2 times 3 ohms. Ladybug would be at the yellow potential. Then the ladybug walks, walks, jumps across this battery post here. That's going to be an increase in potential by 6 volts. So plus 6 volts, and we're back to where we started. So I'm going to put equals 0. So there's my first equation I can use to solve this problem. Now, keep in mind that this is the loop we just did, right there. Right now, I'm going to do another loop. And I've got two choices. I could either do this little loop or I could do the outer loop, either one. I'm going to go ahead and do the smaller loop. So I'm going to imagine my ladybug starts here and goes around this loop clockwise. So as the ladybug's walking, here's the first potential difference it would hit. It would drop in potential by 6 volts. So we're going to minus 6 volts for that first term. Now the ladybug is at yellow potential. Now the ladybug walks, 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 jumps across this resistor. Now there's a potential difference here. See how we're going from yellow to orange? That's going to be an increase in potential. All right, see how we're going into the current in my picture by an amount I2 times 3 ohms. And again, that's Ohm's law. Voltage equals current times resistance. So our ladybug would be at our orange potential here. So ladybug walks, walks, walks along this path. Now when that ladybug goes across this part of the problem, that's going to be a drop in potential. Now it's important to know why. So look at my I3 I have drawn. I've assumed it's kind of down, which over here would be left. So if we move from right to left, we are dropping in potential. All right, basically when you write these equations, anytime you're moving with the current, you're dropping in potential. Against the current, you're going up in potential. So this is going to be a drop in potential by an amount I3 times 1 ohm. And then we're back to where we started, so equals 0. Now, one thing I'd like to point out, it might be tempting now to write an equation for the outer loop, but you'll notice that, all right, we did this loop, then we did this loop. And you notice that everything's covered here now. We've basically worked the whole circuit over, so to speak. When you're writing these system of equations, you got to be careful. It's very easy to all of a sudden write another equation that isn't actually a new equation. If I do the outer loop, what happens is I'm going to get an equation that's really what's called a linear combination of one of the first two equations, and you don't actually get a third new one. So you have to use a new type of equation. The other type of equation we can write for these problems is basically conservation of charge. They're called junction equations. If I take a look at like this junction right here where these circuits come together, coming into that junction is the current I1 and going out is I2 and I3. So I can write an equation that says basically the current's coming in, I1, equals the current's going out, I2 plus I3. Right? What I have now is a system of equations for I1, I2, and I3 that can be solved to find I1, I2, I3. I'm not going to do that in this video. The point of this video is how to write the equations. So let me kind of summarize this. What you do, first, you typically sum up all the delta V's and they have to equal 0 in any closed loop. And what a closed loop basically means is if I start here, you have to end here. You typically, what I like to do is write equations until the entire circuit has been covered, and then usually you'll write at least one. In a complex problem, you might need to write more than one. You write a junction equation where the sum of all the currents in is equal to the sum of all the currents out. So again, this video is just meant to be a video on how to write the equations, and basically this is how, right here. I like to color code them first. That's not necessary. You do have to draw the currents first, though. You assume current directions. Right? If you know them, put them in their correct direction, assuming positive charge carriers going from higher to lower potential. If you don't know a current direction, guess and move on. And just be very consistent when you write your system of equations. So, hope this video helps give an idea how to write Kirchhoff's, or how to apply Kirchhoff's laws. Have a great day.